Hello, I'm Pablo Arregui, a professor at University Paris-Saclay, and I will very briefly outline an archive paper called Quantum Networks Theory. This paper is all about quantum superpositions of networks where even the connectivity of the nodes and the population of the nodes can be in a superposition. This is joint work with
Amélia Durbec
and Matt Wilson.
But there are really two main ideas, and so I want to quickly describe these two. The first one being the concept of a generalized tensor product and partial trace. So traditionally you consider some white node here that's named A, that belongs to the Hilbert space A, and the usual tensor product would take something from that Hilbert space A, something from the Hilbert space B, for instance that black node B, and build something that belongs to the tensor product Hilbert space AB, in this case a white and a black node. A nice feature of the good usual tensor product is that it lets you write things like U tensored I, where it's very clear that U is acting left of the tensor, that is, it's applying upon node A only. Now, this node A is really a network per se, and in that sense it belongs to the larger Hilbert space of every possible superposition of every possible network, just like this is a possible network too, which belongs to that same H. So we may wonder, what if we want to define a tensor product that's a binary operator over that entire large space of every possible network? Well, if you ponder this question seriously, you will see that a number of problems arise. For instance, what would be the result of the black node B tensored with the white node A? Would it be the same as what we had before, just that network? But if that's the case, then this U tensored with I, where does it apply? To B? Worse even, let's say we take the tensor product of a network with itself. Is that even well defined? If you want to define this generalized tensor network, we will need to solve these issues. So here is our solution to that. We are going to parameterize the tensor product by this chi. Chi is a function from networks to networks, and in particular this chi A here is selecting that part of the network which has node A. Then we shall say that this tensor product here has to be sent to the null vector, because it is never the case that chi A would select a B node to go to the left hand side. In the same way, this tensor product has to go to the null vector again, because there is no way chi A would leave out a node A to go to the right hand side. This is clearly unambiguous. If you do that and you write U tensored with I, then it is clear that the U will act upon the A node. So that is all nice, but now we may wonder, what are all the possible chi's that are allowed? This one discriminates on names. It looks for name A, but would it be possible that we could come up with a chi that discriminates on whether we are white or black, or whether we are close to a black, or something like that? And it turns out that we can very well do that. We can parameterize the tensor by this little function mu here, which is basically selecting the wide part of the network, and that will work just as well, and you'll have that the tensor of a white node with two black nodes is a white and two blacks, etc. In general, these chi's can be almost anything. They just need to meet this little condition here that says that if some network H is in between G chi, the restriction of G under the chi, and G itself, then H chi has to be equal to G chi. We call these things restrictions, and it just works. These generalized tensor products are rather expressive. They are, of course, extended by bilinearity, and that lets you write things like this equality here, where you will find that one single state can be either a product state according to this chi AB here, and an entangled state if you view it from the point of view of the mu restriction. For every possible restriction chi, you not only have a tensor product, but you also have a partial trace along chi, which is defined that way. Well, this is the row traced out just to keep chi. The way it works is that you will restrict G and H over chi, and you will compare the rest of the graphs to see if they match. This notion of a trace out enjoys being linear by definition. I mean, it's extended by linearity starting from this formula, but it's also completely positive and trace preserving. Also, any restriction chi induces a robust notion of locality. To be chi local intuitively means that you're not touching the rest of the network, you're just ignoring it. You are going to modify the chi part of it. And there are several ways to state that. The definition that you have to take at the beginning is to say that the amplitude of transitioning between some graph G and a graph H is expressed that way, i.e. you will not transition if you don't leave the rest unchanged, and your amplitudes of transition must only depend on what's happening in that cylinder here. But there are other ways that are more operational. Here you're saying that basically A is acting solely on the chi part and as the identity on the rest, and that expression here stems from the Heisenberg picture, where you view A not so much as an operation but rather as an observable, and you're saying if A is local, well, really it's only observing the chi part of the state row, and so the result of a measurement should only ever depend on the reduced density matrix at chi. If you now give me not just one but two restrictions, chi and zeta, well, we can now express a robust notion of causality. Causality is the idea that some global operator U that acts this time over the entire network and can really change everything at once still obeys a constraint, which is that the zeta part of the image is a function of the chi part of the antecedent. The effects in zeta only depend on the causes in chi. The way you would write that is this way. i.e. the partial trace on zeta of the result really only depends on the partial trace along chi of the antecedent. And there are again alternative ways of saying this. For instance, in the Heisenberg picture, in terms of observables, you would tend to say that at t plus 1, if you observe A along zeta, well, this is equivalent to having observed something at time t along a slightly bigger region, that of the causes of what's happening later in zeta. And so, therefore, it corresponds to observing something that is k local at t. Yet another way of formulating this in a more operational fashion is to say that you should decompose into several parallel chi local gates, and that is something that we prove also. And so altogether, that is it. We have shown that any restriction chi leads to an expressive tensor product, a partial trace, a robust notion of locality, a robust notion of causality. That was the first main idea I wanted to give some overview for. Our second important contribution is to have made this work over arbitrary quantum superpositions of graphs, including superpositions of connectivity and node population, that is allowing for dynamics that create vertices, distract them, change the graph, etc. Let me go into this. Let me do this by introducing to you the two problems that gave us a lot of headache at the beginning. Consider that network here and that one. Well, the sole difference is that here node A and node B are connected. Now, let us go back to the question of defining this tensor product over entire networks. What ought to be the result of tensoring node A with node B? Should it be this graph or that one? Well, perhaps the question is even more striking if I ask it the other way around. Let's say that I decompose this along chi A. Surely I ought to get this, but now what if I decompose this along chi A? Should I get this again? And in this case, where is the connectivity information gone? Right. The second problem that we had is, suppose that you have a unitary evolution over your Hilbert space of networks, which is one that takes a single node A and creates a new node. How should you call that new node? Should you call it B or C? But if U is unitary, then it should have an inverse. If you call it B and that goes back to A, or call it C and that again goes back to A, then you can't be unitary for sure, because you're dropping the second name and that would be reversible. So two problems that we needed to solve, and let's look at how to do that. So, regarding the first issue, the where are the edges gone issue, our fix is to use the names of the nodes to hold the geometry. We have little operators here on the names, and if you see a minus zeta somewhere and a zeta elsewhere, it means that the two nodes are connected. So here they are connected, and here, even though they are separate, if you bring them together with the tensor product, the edge information will be again induced from the naming. In order to solve the reversibility of the names issue, we use a solution from reversible causal graph dynamics, introducing two new unary operators, .L and .R. Basically, we're saying that if you split into two nodes, well, its infants will be called U.L and U.R. And so what happens when you now apply U-dagger? Well, U-dagger is really an operation that merges nodes, and in that case you want to use this merger V operator, right? But if you apply U-dagger to the results of U here, then what you get is the merger of U.L with U.R, and you know that this ought to be equal to U. Therefore, U is equal to U.L merged with U.R. That is, these operators here have a notion of equality. They really form a... The nice thing is, once you set this up correctly, these name algebras and equalities, etc., then everything follows. All of the previous results carry through. That was the main idea of the second contribution, a thing that allows for these superpositions of networks to grow, destroy nodes, change their connectivity, etc. This whole thing gives you the mathematical artillery to talk in a rigorous way about evolving quantum networks, whether you want to talk about quantum internet, quantum gravity, quantum complex systems, or simply think about what is a computer ultimately, something that would use both spatial parallelism and quantum parallelism in a unified model of computation. Thank you.